Heavenly Father, thank you for this day and for what you're doing in our lives. Thank you for the ministry of grace that really does happen. It's just incredible how you lead us in the paths of righteousness for your name's sake. And it's not religious at all. It's freedom to the max. And thank you, Jesus, for providing that. Through your own blood, you did it. You gave a gift that's beyond what we can comprehend. So Lord, help us to embrace that gift, to take every part of it that you've got prepared for us. I pray you do that for this class. In Jesus' name, amen. Okay, you're not going to have this on your notes, but it doesn't necessarily mean that you can just zone out. So this is talking about visible light scattering. And you see that all the time. In fact, you look out this window and you're seeing it happen. It's happening right now, right as we're sitting in this room. We're in this room, it's happening all over out there. So the sun, our sun, that big thing you're not supposed to look directly at, sends out electromagnetic waves, and it sends them from X-rays, and X-rays are 7.874 hundredths of a millionth of an inch, little teeny. Their wavelengths are really, they're very, very small. Up to about 10 meters, which is 33 feet, radio kind of waves. So it sends out all that kind of energy. Electromagnetic energy, that's what it calls, it sends it out. So it sends it out, but it sends out more of some than the other. It sends it all out, but more around the 520 nanometer range. So it sends more of the range. This is 500, this is 520, 40, 60, 86. So right around this range, it's kind of greeny violet, right in this range. It sends more out at that wavelength, the sun does. But we don't see it because this green isn't scattered the way blue is. It sends out violet, but it sends out relatively smaller amounts of violet. But it sends a lot out this, and so because it sends out so much, and the particulates in the air, the molecules and stuff in the air, scatter that blue. So that's why the sky is blue. It's little, it's the wavelength, the blue wavelength, right here around 500 nanometers. The majority of, the greatest portion is this green area, but right around here in the blue, that's what gets scattered, and that's why the sky is blue. So 99% of the sun's rays that it sends out happen to be in the visible light range. Now, isn't that interesting? That would be the one range that you and I would see. Out of all the range, out of all the stuff it could send out, it sends out most in that wavelength that you and I can see. So air molecules, it's those little guys that scatter the incoming light. It's white as it comes, but the air scatters the blue in greater amounts. It doesn't scatter the long wavelengths during the day. But in the evening, where the sun is lower, let's say this blue is our atmosphere. And so, as the sun shines, and if we're here, and it's shining all the way through. It's not just shining through this much atmosphere, it's shining through a much greater range of atmosphere, which scatters more of the incoming wavelength. So the shorter stuff gets scattered, and the longer stuff remains. And the longer stuff is like the reds and the oranges and the yellows. That's why at sunset, you get more of that, because the sun's rays are traveling through more atmosphere, and there's more molecules and other particulate matter that can scatter that stuff. So there are clouds and there are blue skies, and I had somebody, actually, it was Rachel over from Mount Carmel was in my class 2 years ago, and she asked the question in class, not only she didn't ask why are sky blue, but she asked why are clouds white. I didn't know. I'd never even been asked that question. I'd never thought about that question. Well, the sun's rays, as is in this example, it sends out white light, and it's scattered in all directions. The clouds scatter it like that. They don't diffuse it, they scatter it. So in every direction. So it comes in as white light, it goes out as white. It's not like a prism that scatters it in colors. It comes in as white light, it's scattered in white light. However, when you have clouds like this that are dark, that you say, looks like rain, it's because the reason why these are like this is because they're little droplets in the clouds. In fact, clouds are condensed, so you have little droplets. But generally speaking, the average cloud like that you got, I think we have some right out there. Yep, they're just smiling at us up there. So there's not any significant amount of heavily or large sized pieces of moisture in those things. So they're not, lights just come through. But when you get moisture, it starts to reflect back. Or if you have clouds on clouds. And so the light from the sky, what you are seeing here in the dark is shadows of the rain or ice that the clouds are containing. That's why when the clouds are dark, you can say, it's rain coming. And it's because the sunlight isn't penetrating through. If you're flying, you see white clouds all the time. You are flying over them. I mean, that's one of the neatest things. I really like to fly, because I can look down and see clouds, just all kinds of shapes of clouds. In the sunset, you see sunsets like, wow, they're just incredible. You can see storms if they're down below you. You see storms happening, you see the lightning flashing and stuff, you can see it from above. It's really cool. And you can't do anything up there. You can worry, but it's fruitless. If you're gonna go down, you're gonna go down. So you can't do anything about it, and you might as well just enjoy the ride, which is really nice, if you haven't enjoyed that already. Anyway, so, and this just says, when the sun is low in the sky, rays of sunlight take much longer path through the atmosphere, much longer, more opportunity for light to be scattered and absorbed by the atmosphere, things in the atmosphere. So enough scattering, almost all of the shorter stuff gets scattered or absorbed. It just does, the shorter wavelength. And what's left is along the wavelengths, like the reds and the yellows and the oranges. So that's just, we'll probably talk about that later, but in my endeavor to do this class so that it would have some relevant interest. I mean, you got Earth science. We could talk about geology but probably a very small percentage of you is gonna be interested in what kind of soil we have out there. We can spend a semester talking about it, but I don't think it'd generate interest. But this stuff you're gonna see every day, and so I made an effort to try to incorporate something that is relevant to your everyday kind of living, which is when you have children, if you have children, and they come up and ask, why is the sky is blue? You got it. Why is the sunset orange and red and yellow? Got it. Wow, man, you must know everything. You say, well, yeah, just about. Anyway, so this is page 2 of the 6-page stapled, all those handouts I gave you last time. This is the second page. It's the back of the first page, second page, closer look at visible light. So some of this is a rehash, study of properties of light. They depend on wavelength. They do. So that was one of the questions, that was one of the text questions of this happened. So it's being said a second time. You had it on a test question, you got it on a lecture, you got it here. I'm putting it out, saying that you'll see that again. So the amplitude is the difference from this center line, high, or it's the same here. This would be the same here, and the same here, and the same here, at any given wavelength. So you have the amplitude, you have the crest, crest to crest, or trough to trough. One wavelength can be from here to here, or crest to crest, or trough to trough. They're all the same distance. This distance is the same as this distance, is the same as this distance, as far as how far apart they are. So the spectrum, which produced white light, is passed through a prism. These things bend, this light bends. And the shorter wavelengths bend more. That's why when this light passes through this prism, these are bent more than these. The reds are bent less, they're longer wavelengths. If you could see infrared, if you could see or ultraviolet, you would see this bending less and this bending more. Shorter wavelengths are bent more than the longer ones. So using a prism, light can be separated into its component colors. Visible light. But you've still got, if you got this coming in here, you've also got ultraviolet and infrared. I mean, all this is radiant energy. It's coming. I mean, you and I are generating wavelengths. That's why you can take certain, like if you go out hunting and you got a scope that will cut through the darkness and illuminate whatever is radiating heat. Well, you'll see the whole shape of the deer. The whole deer is radiating heat. And in some places it's radiating more than others. So you can see that. So, the spectroscope. Each color of the spectrum have different wavelengths, you know that. In the visible spectrum, red is the longest, violet is the shortest. The spectroscope is used to separate starlight into its respective colors. And you see here, if this was a source, so our sun, all we see, well, we don't look directly at it, other than to our own peril. I mean, we can do it, but to our own peril. So if this looks yellow, and it comes into a spectroscope, it will be reflected back to this kind of a mirror deal, and then, or a prism deal, is reflected back, and it will bring, the spectroscope will lay it out like this. And the colors that it breaks down to, this is hydrogen, this is, well, sodium, yeah. Mm-hmm. And magnesium, I was thinking of, yeah. So these are, you can tell that this is a black line. So where the black lines appear, it indicates that that this source that looks just like one thing can be broken down into its color scheme, which then have black lines that delineate which chemicals it contains. So that's what a spectroscope does. In astronomers, they can determine the chemical elements, as it illustrated in that thing, the temperature, pressure, magnetic field, and conditions of the gases of the star, can determine all of that, and the distance between the Earth and the star, if it's increasing or decreasing. If it increases, it's a red shift. If it decreases, if it's coming toward us, it's a blue shift. But if it goes away from us, if it's going out there, it's a red shift. And they can tell, I don't know how they delineate it, I haven't looked it up, but as Jason Lyle, or Leslie said last time in the short clip I showed you, they're talking about a redshift 14 being what scientists would have thought would be really close to the beginning of the Big Bang. I mean, not at it, but they shouldn't be able to see much beyond redshift 14. Well, they've been able to. They've gone beyond that. But redshift 14 is a marker of how far it is away from where we are and how close to what they believe would be the Big Bang to be. So redshift 14, well, they saw complete full galaxies at that redshift level, so they had to revise their thinking about what went on to create them. Anyway, so I don't know I don't know how far away each of the, you could probably Google it, to find how far away each, like redshift 1, 2, 3, 4, 5, what amount of distance they're covering. I should do that. But the three kinds of physical spectrum, as we reviewed in test question 6, three kinds: continuous, bright line, and dark line. You can read a lot about this. I'm just going to want you to know something. A continuous spectrum is an unbroken band of colors. A bright line is an emission spectrum. So even the series of different colors of brightness come from chemical elements when they are in their form of glowing glass or vapor. You can read that on that sheet. Different wavelengths appear as bright lines at different places in the spectrum. A dark line spectrum is absorption. Bright line is emission, like emitting. Dark line is absorbing, sucking in, absorbing. The dark line absorbs this. And we get dark lines where light or radiant energy is absorbed. So an incandescent hot or radiant energy emitting source sends energy through a cooler gas under low pressure. Cooler gas absorbs certain wavelengths. These are absorbed wavelengths, can be seen as black lines, as was shown up there. Different gases absorb different wavelengths, so it kind of is a fingerprint of what you got. Which, there you go. Dark lines are in exactly the same place as the bright lines, from the same element in a bright line spectrum. So it reveals the composition of the star's outer layer or the planet's atmosphere. So dark lines and bright lines would appear in the same place. So there we go to galaxies. That's the one. Next one. Yo. Okay. Galaxy is an immense cloud of hundreds of millions to hundreds of billions of stars. It's hard to comprehend that one galaxy could contain billions of stars. And our sun is a star. It's a medium, it's bright, it's a lower medium, it's not the brightest, it's not the dimmest, it's right in the middle range of it. An average star, size star, but they can be hundreds of billions. Some of them are huge, well, like that, when we watched the video we saw when you came in here what's his name, Louis Giglio. And he showed the comparison. In fact, there are a number of comparisons online that you can see of the stars and the ones in this solar system. I mean, there are some that are as large and they would dwarf our solar system. That they were not only as big as our sun, but as big as the orbit of some of the largest planets, or some of the rotating planets around us, like Uranus or Neptune. They would be large enough to encompass all of those in their size. And that's just in our own solar system, let alone the billions of solar systems that are out there. It is astronomical. So each star moves in its own orbit, held within the galaxy by the combined gravitational force of all the other stars. Each galaxy, apart from those few undergoing collisions, is therefore an independent and isolated star system. Although they think of it in clusters, they're clusters. I think we're part of a 30 galaxy cluster. But our nearest galaxy is the Andromeda galaxy, and that's about 2.52 million light years away. So 58 trillion times 5.5 or 2.52 million, and you get the amount of miles. Lots. Just lots. Don't plan to go there very soon. Huh. I wonder what people would see in heaven. If they would be able to if they would have a view of God's creation and understand that they would be able to understand not just the largeness of it, but the magnificence of it. I mean, we look at this, these are all galaxies. I mean, this is a picture of this, but all these, when they point them out, they say, well, this looks like a star, and this may be big enough to be a big star, and this might be a galaxy, it looks kind of like, but all these are galaxies. They're galaxies with hundreds of billions of stars in them. It just, I mean, I can't comprehend how magnificent. It's just, wow. I mean, I go outside and see the stars that we have. You go, whoa, look at that. It's really pretty. And when you don't have any lights shining around you, I mean, when the electricity go off so we don't have lights on the poles, I mean, looking at the night, going up on the hill by where the zip line is, it's just beautiful. Just incredible. But that's nothing. Well, it is something. It's incredible. But that God has created these things, and they're so massive. So the Hubble Deep Field Telescope, that's what we've got at about, what is it? 352 miles, it's orbiting around the Earth. Taken over a time period of a year, was pointed at a single piece of sky for over several months, a spot covering less than 1/10 of 1/1,000,000th of the sky. So you got 1/1,000,000th of the sky, and you got 1/10 of that. So there'd be 10 parts of that. Then there were about 10,000 galaxies visible. Extrapolating that postage stamp piece of the sky for the whole sky would give you mind-boggling of wood. Just big. James Webb Telescope sees further into space than the Hubble, and has exposed hundreds, and probably a lot more than that, of unknown galaxies. Milky Way, where our sun is one star among roughly 200 billion. Estimates range from 100 to 400 billion stars in our Milky Way galaxy, just where we are. Belongs to a small cluster of about 30 galaxies, which is a local group. Excuse me. Our nearest neighbor, the Andromeda galaxy, contains about 1 trillion stars, has a radius of 69,600 light years, plus or minus 3,900. Well, you know, there's flexible in there. I mean, what we're doing at that to estimate that, I don't know, it's pretty boggling. It's hard to estimate where we are because we're there. And we've just sent, they were sent out in 1977, Voyager 1 and Voyager 2, spent from 77 to 2012 to get to the edge of our solar system. That's just our solar system. And they're still going out, so they're outside of our solar system now. So that's just our solar system as one, maybe 1 to 400 billion stars. So we're looking at this Milky Way from inside it. So it's hard to really get a picture. We can't go up and stand and look down and count and say, okay, we can give an accurate count here. We've got 382 billion stars here. We're not doing that because we can't get out of here. So there are places we just have to estimate. Anyway, much of our ignorance about galaxies can be attributed to their great distances from us, how far away they are. So Edwin Hubble, whom that Hubble Space Telescope is named after, began in the 20s, did a lot of research on the shapes of galaxies. So he was looking into that thing, spent a lot of time looking into that thing, and he classified these galaxies into 3 kinds: spirals, ellipticals, and irregulars. And so these are a left picture of what. This doesn't necessarily look too elliptical, but you can assume that it is. And irregulars are this. Now this looks a spiral. This is irregular. This is a spiral. This is a spiral. And one of the things about creation, if Jason Lyle or Leslie was correct, then in the early part of shortly after the Big Bang, you wouldn't see any of these because it's taken a while for these to form, and the older they are, the spirals wind up. So you shouldn't expect to see things that apparently the James Webb Telescope was representing. So he had 3 different kinds of 3 categories of spirals. He broke them down into 4 other parts, which I'm not mentioning because they believed that part of what he was hypothesizing, as the galaxy aged, its type or shape changed, he constructed a diagram that made his hypothesis look plausible. So he created something that made things look like he was talking about, except astronomers now believe it was incorrect. He classified the system, however. It is still used as it covers well of the most conspicuous systems. 3/4 of all known galaxies are spirals. Central lens-shaped nucleus made of millions of stars, spiral arms trail behind the galaxy as it rotates. So, 3/4 of all known galaxies are spirals. That's 75%, if you want to know. Okay. So that's that. That's that. And are we on stars now?
Yep.
Okay. So, a star's spectrum is a record of the amount of energy the star emits at each wavelength. That's what a spectrum is. A record of the amount of energy the star emits at each wavelength. And perhaps the single most important thing we can know about the star. Whoa, I'd circle that if you're circling. If you online are not circling, you should just plug it into your brain. Say, okay, when I get to stars, this should be circled. The spectrum tells us the star's composition, what chemicals compose it. It tells us the temperature and the luminosity. It also talks about velocity in space, rotational speed, and other properties. But three that I thought were significant: composition, temperature, and luminosity. We're going to talk about that here shortly. Almost all stars are made of the same mix of elements, but differing conditions result in different spectra. So they basically made of the same thing, except they're different amounts, same kind, but different amounts and under different conditions. Temperature of the stars. Stars are very hot. Earthly standards, the surface of temperatures of even the coolest stars are far above the temperatures that most substances vaporize. Not melt, but go vaporize. So using a physical probe to take the star's temperature would not succeed. We'd have to do it some other way. So astronomers use indirect methods. Temperatures can be deduced by the color of light emitted. Hotter objects emit more blue light than red. So what would that indicate? Why do you think that would tell something about the difference in heat? Because the shorter wavelength elements are more energetic and generate more heat. That's like gamma rays are extremely energetic, and they can penetrate through us and do damage in what they come into. Yeah.
So is that a similar reason as to why, like, when you look at a flame, like, produced by, like, a butane light, there's a blue layer at the bottom before it gets to the red?
Yeah.
That's cool.
Yeah. It's hotter there. And so, and that's why, because temperature, heat is still being emitted. If you've ever seen a piece of steel in a forge where somebody's beating it and it gets really white hot, and then they beat it and beat it and beat it, and then they put it into the, and if you just let it sit there and it cooled down, pretty soon you would see no color on it. But if you grabbed it, it would burn your hand badly, because it's still generating heat even though you don't see it. So this, they use an indirect method, which is Wien's law. Now Wien's law, this is pretty simple algebra. So temperature, the temperature in degrees Kelvin, that's a measuring, you have Fahrenheit, Celsius, you have Kelvin. Kelvin is just a measurement. It's not, you don't have to think about, well, what is it going to be? It's just the temperature is equal to this constant, 3 times 10 to the 6th, which is this. So there's 1,000, 10,000, 100,000, 3 million. Divided by this. So, the larger this is, the larger this little alpha is, or this, not alpha, sorry. The larger this lambda is, this little notation is. If you divide this into this, if this was 1, this would be this. If it was 2, this would be less by half. So the bigger this is, the smaller the temperature would be. That's what you get. And there's a wavelength in nanometers at which it radiates most strongly. So our sun, lambda, would be the wavelength that it radiates most strongly, which would be at 520 nanometers, right around the green range. It would be, that's where most of the radiant energy coming from the sun is. Not all, it goes from gamma to radio waves, but the most of it comes right in that, about 520 nanometers, which is a green range. And so you would have, what you pick up most it's radiated most strongly, and you divide that into this formula. You divide 2,520 nanometers into this, and you would get the approximate temperature at the surface. So the longer the wavelength, so this is a green range for the sun. If it was red and the wavelength was longer, the longer the wavelength of maximum emitted energy, the lower the temperature. Longer the wavelength, lower the temperature. Longer the wavelength, lower the temperature. So this says, the longer the wavelength, if it's more here, it makes this value less. Because you divide more into this, the number gets smaller. Okay. The numerator, the top number is fixed. This doesn't change. This doesn't change. It's just this that changes, and that's what you get the temperature. Whatever this is, you divide this into this, you get the temperature. So the longer this is, longer the wavelength is, you got a bigger value to divide into this, and that's what you didn't know.
So you said most of them are 520 nanometers?
Well, the sun, our sun, right, that we don't want to look at, our sun radiates from a range of, well, gamma rays to waves around 33 feet long. Now, it doesn't radiate 6 mile, I mean, there are some objects that radiate radio waves that are something 6 miles between crests, but not our sun. That we know what our sun is radiating. But most of the energy, the large portion of wavelength size that our sun radiates is in the green range, which would be so it would be right here. The largest portion of energy. So it's radiating all kinds of energy from gamma rays to radio waves, but the largest portion of it, because it's what it's composed of, is right here in this green range. So if you're dividing this by which would be in the violet range, and if you're dividing it by 700, which is in the red range. So if it was emitting at the violet end, which is hotter, then dividing 400 into this would give you a larger number than if you divide this by 700. So the hotter it is, the higher the temperature, the smaller the nanometers, and this would be wavelength. Well, how many times this wave passes in a second? But let's just say it's like this. And this one so this is larger, means this is traveling slower, which means it's cooler. Red is cooler than the violet. So if you divide that in, is that? Huh? Yes.
So the denominator is the wavelength, and the numerator is What is that?
That's a constant. That's just a constant. Scientists have figured out, I didn't figure it out, scientists have figured out that this constant, if they use this formula, they can find the temperature. They can find that the temperature that they could say of this star is, not every part of the star, because underneath it is even hotter, but what the outside of it is, the temperature is this constant divided by the greatest amount of radiant energy coming out of it. And our sun emits the greatest amount of radiant energy in this green range. So you'd be dividing it by somewhere in here. There are stars that would radiate this amount, so you divide it by this. You say, okay, this is a cooler star than a star that does this. And our sun is right here in terms of the temperature in degrees Kelvin. So that's what that is. Just be. So that's what we got. Star brightness. So now we're on star brightness. The apparent magnitude. Apparent magnitude. Apparent. Apparent means not one of two. It means something that appears to be. Okay, it looks like it's about 63 degrees outside. It's apparent to me that that's about what it is. I don't know how hot it is. I don't know what it is. But if I look at the sun and I think, okay, it felt like this when I came in this building. There was wind, but I felt whatever. Apparent is something that appears to be. And there is an apparent, what appears to be scale, invented by this Greek astronomer Hipparchus. Hipparchus. Something like that. He's not here to correct me. 150 BC. He ranked the stars he could see in terms of their brightness, with 1 being brightest and 6 being faintest. That's what he did. So he looked at the stars. I don't know what he was looking through, but he was looking at the stars and said, well, okay, this one's real bright, and this one's not as bright. So the brightest, he says, were 1, and the lesser were 6. That was 150 BC. So modern astronomy has extended this apparent brightness scale to include our sun. Now our sun then, at minus 26.7, so he said there was 1 for bright and 6 for dim. That was his scale, 1 to 6. So we've taken that scale, or somebody has, I don't know who they were, but they took this scale and they've expanded it. And they say, we look at our sun and it appears to be, this is what it looks like. It's not what it is, but it looks like. Okay? Apparent is what it looks like it is, not what it is. We'll find out what it is shortly. But what it looks like is a negative 26.7. I mean, way down the scale. I mean, here's this scale, and it's way over here. Because it's right there. I mean, it's so close. 93 plus or minus million miles away. So, and the very dimmest is a plus 16. So, we can go way over here to plus 16. So this is really dim. He could see 1 to 6. We can go to plus 16, which is really, really dim. Apparent magnitude is simply how bright the star appears to us on Earth. It does not tell how hot it is. It doesn't tell how bright it's shining. It doesn't tell how big it is. It just says How does it look? How does it look to you? Oh, that's bright. That's not as bright. That's even less bright, and that's more bright. So it's how it looks. So that's why it's called apparent, looks like. Three factors control the apparent brightness. Need to know these. How big the star is, how hot it is, and how far away. Because our sun is really close to us, really close. In fact, the closest star next to our sun, as I said, was 2.52 million light years.
Million.
Was it million?
Million.
Almost right.
That's the closest star. That's a long way away. So our sun is right in our face. And so it looks big because it's close. It is big. And it's hot. It's about mid-range hot. But it appears to be the biggest thing around. That's because of its closest. So, from the Earth, the largest star would tend to appear to be the brightest, assuming they produced the same amount of radiant energy, even though it might be farther away. So if these stars all produce, if Betelgeuse, that huge one, all produce the same amount of energy, the one that their size would depend on how close they were. We have a way of measuring this. So a first magnitude star is 2.5 times brighter than a second, and a first star is 100 times brighter than the sixth. So a star can have 0 magnitude, like if we could go to negative 26.7, then you can certainly have a 0, which doesn't mean it doesn't have any brightness, it just has the scale has been expanded to go into the negative. Sirius, the brightest star in our sky, has an apparent magnitude of -1.4. That's what it looks like when we're standing on Earth and it's standing there. It's not standing. It's moving and we're moving. We're all moving. We're moving really fast. But when we look at that thing, that's what it looks like. That's in the brightness scale, that's what it appears to be. Actually, outside our solar system, there are only 4 stars appearing bright enough to have negative values. Our moon, reflecting the sun's light, can reach an apparent magnitude of about -13. And it just reflects the light. It doesn't generate its own. It reflects the light off the sun, and it can be as bright as a -13. So that's our moon. It can get up to -13. Because apparent magnitude of a star depends on its distance from Earth and its luminosity. The moon is very, very close compared to the stars. 4.24 light years. The Andromeda Galaxy was 2.52 billion light years. So 4.24 light years is the nearest star. I'm sorry, 4.42 light years. So 4.42 times 5.8 trillion miles is a long way away. Anyway, but it's the closest. Luminosity is related to the amount of energy a body radiates each second. It is the actual true brightness of the star. So luminosity is a true brightness. Excuse me. Luminosity is the true brightness of the star. It depends only on the size and temperature. So it doesn't depend on how far away it is. It depends on its size and temperature.